we will draw the band diagram. There is an easy way to draw, don't confuse. If you follow these steps, you can draw band diagram of any semiconductor. Okay, first when we are taking p type and here n type, so we know clearly this p type means here Fermi level is close to the valence band, and here n type also we know clearly Fermi level is close to the conduction band. Okay, this is the difference between energy levels. This is the band gap, EG or energy gap. Here also you can say the difference between these two energy levels, EC minus EV. EC minus EV is the equal to energy gap. Okay, this is energy gap, and if you combine, there is a interface. First you draw the interface. This is the sorry, I will draw correct straight line. Just it's not a straight line. So I am drawing a straight line, that is interface. Okay, this is interface of between two semiconductors. Interface between two p and n type semiconductor. So equilibrium condition, what happens? The Fermi level is constant throughout the semiconductor. Why? Because suppose here see, you have a one beaker, here you have a one beaker. Suppose water level is, suppose here water level is high. Suppose here water level is high. This is just water level is indicates a just like Fermi level. Here water is just like a electrons or whatever you can say. Okay, here also water level is here. So this is also just like Fermi level. Okay, just like Fermi level. When you combine this one, so what happens after when you combine these two one, here electrons are higher or water are higher, so water will flow to this beaker, and after that here also water is equal and here is also water equal. Then there is no flow of water from one beaker to other beaker. That means where is this water level? Here, some height. Okay, it is here also water level is at some height. So this water level is equal in both beakers. Similarly, water level equal. Similarly, Fermi level also equal in both semiconductor at equilibrium condition. Okay, did you get this point? Do you understand this one?
Yes, sir.
So Fermi level is equal, like water is equal level at equilibrium condition, or in this case water is up to some height h. Okay, here also water is up to some height h. This level we are indicating similar comparison to Fermi level in a semiconductor. So at equilibrium condition, the Fermi level is constant throughout the semiconductor. This is the, okay, this we will draw. Okay, after interface you have to draw Fermi level, constant Fermi level at the equilibrium condition. So remember, we are drawing at equilibrium condition. Fermi level is drawing at. So I am drawing Fermi level is constant throughout the semiconductor. First we have drawn interface. Second we have drawn Fermi level. Right? Fermi level we have drawn. So for n type, this is n type and this is p type. So this is Fermi level. Yeah, this side also Fermi level. So for p type semiconductor, Fermi level is close to what? In p type semiconductor.
Conduction band.
In p types. I'm asking in p. Yeah, valency band. So same thing. Draw it here. Just you draw this one. This is valence band EV. Okay. So conduction band is away from the Fermi level, right? Just you draw same as it is. For n type semiconductor, how where the Fermi level lies near to, yeah, right, very good. So near the conduction band you draw it like this, and valence band is away from the conduction band. Just we have drawn interface and Fermi level. After that we have drawn these levels. Okay, so after that just you join these levels, conduction band to conduction band and valence band to valence band. So what we have done after that, we have connected this EC to EC and EV to EV. Okay, this is EV and this is also EV. Just we have first drawn the interface. After that Fermi level. After that we have drawn this EC and EV, and here also EC EV. After that we have connected. This is the Fermi. This is the energy band diagram of a PN junction semiconductor, PN junction diode. Okay, it is where it is. It is equilibrium condition. That's why Fermi level is constant. Okay, equilibrium. So now this is the depletion region. Whatever we have discussed, just before. This is the depletion region. This region we call depletion region. Okay, depletion region. Okay, depletion region, and here also electric field is in this direction, internal electric field. Okay, because of this one, here see, here some electrons are there, free electrons are there in the conduction band, and here free holes are there, right? In p-type semiconductor, free holes are there, that is valence band, and free electrons available in conduction band. See here, once the equilibrium is forming, so these electrons are seeing this height, some height is seeing. These electrons, they want to cross barrier, but they are seeing some barrier height. This barrier height is called potential barrier or built-in potential, VBI. Okay, you got it. What is the built-in potential? Once the semiconductor junction is forming, because of this electric field, there is a built-in potential. These electrons, after forming the junction, after forming the depletion region, the electrons, whatever free electrons in n-type semiconductor, wants to diffuse to p-type semiconductor, but they are seeing some barrier height. They are seeing some barrier height. They have to cross this barrier, then only they will enter into this semiconductor. And similarly, here holes also seeing some barrier, this much barrier height they are seeing. So once they want to go into n-type semiconductor, holes should cross this barrier height. Here also you can same thing. This is built-in potential towards p-type semiconductor, VBI. VBI are potential barrier, are you can say height. Barrier means what? Barrier means, what is the meaning of barrier? It is some obstacle, right? Barrier means it is some obstacle. Here also obstacle are some height or some potential. Potential means height only, right? So here see, these holes are seeing some potential to cross this barrier. That's why in after forming equilibrium condition, these electrons will not diffuse and holes also not diffuse. Okay, if they want to diffuse, they have to get some energy. How they get energy? Will give in forward bias condition or will give in reverse bias condition. That means we are applying some external electric field to this junction. That means these electrons holes are getting some energy by external voltage or external field. Then only they will get energy and they will overcome this barrier, or they will climb this barrier, or they will climb this potential. Okay, is this clear to you? What is the built-in potential means? Built-in potential means there is a some height. There is a some height in the depletion region. If the electrons want to cross the junction depletion region, they have to overcome this potential barrier, overcome to this depletion width. Then only they will enter into p-type semiconductor, or holes they may enter into n-type semiconductor. This is the in equilibrium condition